We're live. So, hello, people. Welcome back to the Latin American webinars on physics. This is Joel Jones again from the PUCP in Peru. Our webinar today is given by Gabriel Zapata, who is a postdoc here at the PUCP. This is webinar 179, and Gabriel will tell us about a recent work of his and some collaborators where he proves possible interactions between dark matter and high-energy neutrinos coming from blazars. Gabriel completed his PhD in Argentina at the Universidad Nacional del Mar del Plata, which is not La Plata, as he has taught us very well to understand. Right? And well, he's currently doing his first postdoc here in Peru. So, of course, I am absolutely thrilled of having him participate in law physics as a speaker. Anyway, before we begin, let me remind the viewers that you can ask questions and make comments via the YouTube live chat system. And these questions will be passed on to Gabriel at the end of the webinar. So please feel free to begin with the talk.
Okay, I'm gonna share my screen. You can see the slides?
Everything
Okay,
good?
great. Okay, I will start. Okay, hello everyone. I am Gabriel Zapata, a postdoctoral researcher at the Sección Física of the PUCP. And today I'm gonna talk about our recent work titled Bounds on Neutrino-Dark Matter interactions from the blazar TXS 0506 plus 056 neutrino outburst. That is a work we made with Joel Jones Perez and Alberto Medina, all from the Sección Física of the PUCP. And it's already uploaded to the archive. Okay, so I'll begin with a brief introduction to the motivation behind the work and saying a few words about what blazars are and how we know they emit neutrinos. Then I'll focus on the 2014-2015 neutrino outburst from the blazar TXS detected by IceCube, which is the basis of our analysis, and discuss how we model the neutrino flux during that period. After that, I'll describe the dark matter distribution around the blazar, which plays a key role in determining the attenuation of the neutrino flux due to the dark matter interactions. Finally, I'll present the results and end with a few concluding remarks. So, we have several reasons to believe that dark matter exists and it's all around us in the universe, even though we know very little about these particles. We know that dark matter constitutes about 26% of the total matter energy density content in the current universe, but the normal baryonic matter is just about 55%. So we can see here some of the evidence of dark matter, like the rotation curve of galaxies and the weak lensing effects like in the bullet clusters and the anisotropies in the cosmic microwave background. So in particular, we don't know how or even if the dark matter particles interact with the standard model particles beyond gravity, right? One interesting possibility is that dark matter interacts with neutrinos. This naturally raises the question, how can we study such interaction in a way as model independent as possible? So the basic idea of this work is to use the attenuation of astrophysical neutrino fluxes as they travel through dark matter to constrain neutrino-dark matter interactions. So what we need to do that, we need first a high energy astrophysical neutrino source whose neutrinos have already been detected. We need to have a good theoretical understanding of the possible initial neutrino flux spectrum at the source location. And we need to know the dark matter distribution along the journey of the neutrino to the detector. So IceCube has already detected neutrinos from sources like blazars, active galactic nuclei, and tidal disrupted events. So in particular, our work focuses on blazars. What blazars are? Blazars are a class of active galactic nuclei, which are galaxies with a central supermassive black hole that is actively accreting matter. The matter falling into the black hole forms an accretion disk, which heats up and emits intense radiation across the entire electromagnetic spectrum, from radio to gamma rays. Blazars are a class of IGNs that emits powerful relativistic jets pointed almost directly to the Earth. These jets are composed of high-energy hadrons and leptons, which can interact and generate high-energy emissions, high-energy showers. In particular, hadronic process in the jets can produce pions, which decay into neutrinos and gamma rays. We can see here in this image the bright accretion disk over here, surrounded by this dark torus, and we see here the jets where the pions are produced, and the neutral pions decay into gamma rays, and the charged pions decay into charged leptons and neutrinos, and high energy neutrinos that are after that are detected in the Earth in detectors like IceCube. So blazars have been confirmed as neutrino sources thanks to an event on September 22 of 2017 when IceCube detected a 290 TeV neutrino from the direction of the no blazar, whose direction was consistent with the no blazar TXS 0506 plus 056. Simultaneously, a telescope like Fermilab or MAGIC detected that the blazar was in a flaring state. The significance of this spatial and temporal coincidence was estimated in about 3 sigma. Here you can see the IceCube event track of this neutrino event. And here there's a very nice image that shows the Fermilab gamma ray observation overlapping with the 50% and 90% confidence level contours form the neutrino direction. This event led to 2 papers placing bounds on neutrino-dark matter interactions by Klein and by Ferrer over here. Motivated by this finding, IceCube searched archival data from neutrinos from TXS direction and found an excess of 13 plus minus 5 neutrinos between September 2014 and March 2015. Interestingly, there was no observed electromagnetic flare during this period, making the neutrino odus harder to explain with the standard blazar emission models. These will be the neutrinos we will use in this work. Sorry. So, to constrain dark matter neutrino interactions, we need a model for the neutrino flux from the blazar TXS during this neutrino outburst. So, we start with the flux published by IceCube, which followed this power law over here with an index 2.2 gamma and a reference flux of 1.6 times 10 to the minus 15 TeV inverse times centimeter squared per second. So to validate this, we calculate the expected number of expected neutrino events using the IceCube effective area and find about 50 neutrinos in the window of detection of 158 days, which is consistent with the reported excess of 13 plus minus 5 events. The effective area that we use here is the function that quantifies the detector sensitivity to neutrinos, incorporating the interaction probability and detection efficiency, and depends on the neutrino energy and the reliability direction. For the direction of the blazar TXS, the effective area is shown over here. So this is consistent with, this flux is consistent with the observation. We also searched in the literature for alternative models that fits IceCube observation while respecting limits on X-ray and gamma ray observations. We found 3 such models. The first model of Suetal, that is a 2-zone model where neutrinos and gamma rays are produced in a first zone near the base of the jet, but the most part of the electromagnetic radiation are emitted in a second region further out. X-ray coronal absorption suppresses the gamma ray emission, and this flux predicts 11.5 neutrino events in IceCube. The second model is the model of Wang et al. That is a jet cloud interaction model where the jet collides with a dense gas cloud possibly coming from a tidally disrupted star. The gas increased the pion production and at the same time absorbed the gamma rays to respect the bounds on the gamma ray detection. This model predicts 6.8 EMs. And the third model is the model of Yang et al., where the neutrinos are produced in the accretion disk and not in the jet. This last model predicts 13.3 neutrinos. In this figure below, we show all the 4 fluxes that we use in this work multiplied by the IceCube effective area. That is the integrand of our event counting equation. So we can see here the different shapes that the different spectrum multiplied by the effective area. The next key point to consider is the dark matter distribution around the blazar TXS. So, although the details are technical, the important point is that the adiabatic growing of a black hole steepens the density profile in the inner galactic halo. This creates an overdensity known as the dark matter spike, with a power law steeper than the pre-existing Navarro frame-wide profile, is in the dashed red line, forming this overdensity called the dark matter spike, going from a slope of gamma of 1 to 7/3. Another possibility to be considered is that the gravitational scattering between the dark matter and the stars can dynamically relax the dark matter spike to a lower slope of 3/2. We can normalize the dark matter density profile comparing the mass of this dark matter spike with the black hole mass. Outside of the dark matter spike radius, we consider that the dark matter density profile continues following the pre-existing Navarro frame-wide profile. Also, if the dark matter self-annihilation occurs, the dark matter profile becomes more core, as we can see in this plot over here. The dark matter self-annihilation flattens the density profile, with a maximal density given by this rho max that is equal to the dark matter mass particle over the lifetime of the black hole and the velocity average annihilation cross-section. So, in our work, we consider 2 possible spike slopes, 7/3 and 3/2, and 3 different scenarios for dark matter self-annihilation. No annihilation at all, a weak annihilation of 10 to the minus 28 cubic centimeter per second, and a strong annihilation of 3 times 10 to the minus 26 cubic centimeter per second. This gives us these 6 different benchmark dark matter profiles that we can see here on the right. The importance of this is because the key quantity to the attenuation is the column density. So we need the dark matter to know the dark matter density profile to calculate the column density, which represent how much dark matter particle the neutrinos must pass through on the journey to the Earth. If we consider this emission radius that we see here, the emission radius is the distance from between the black hole and the region where the neutrinos are produced. If we consider this value for the emission radius, we obtain these different values for the different density profiles for the column density. So another important thing is that the contributions from the Milky Way dark matter halo and the intergalactic dark matter are negligible compared with the contribution of the dark matter spike. So, with the neutrino flux and the column density, we can compute the neutrino flux attenuation using this equation known as the cascade equation, which describes how the flux evolves due to the interactions with the dark matter particles. The first term accounts for the neutrino losses, so the neutrinos that get out of the line of sight, while the second term represents the energy redistribution of the neutrino flux due to the down scattering, the dark matter. As a first estimate, we can neglect this second term and consider a cross-section constant with the neutrino energy. And if we do that, we're going to obtain exponential attenuation with the maximum allowed cross-section given by the dark matter particle mass over the column density. This already shows the importance of the dark matter spike. A higher column density puts stronger constraints on the neutrino dark matter cross-section. For instance, in benchmark 1, this limit reached 6 times 10 to the minus 30 centimeters squared for a dark matter particle with a mass of 1 GeV. To refine this calculation, we have to make an assumption on the shape of the cross-section. So we will assume a power law dependence of the cross-section on the neutrino energy. We take the cross-section equal to a reference cross-section sigma 0 times the energy of the neutrinos to the n power, with n taking the values 1, 0, minus 1, and minus 2 values inspired in different simplified modes. We also assume isotropic scattering in the center of mass frame, leading to this simple expression for the differential cross-section. Using these expressions for the cross-section and for the differential cross-section, we can put these expressions on the cascade equation, and with the initial flux, we can obtain the attenuate flux, the observed flux. And with this observed flux, we can put it in this equation over here to calculate the expected number of neutrino events in IceCube using the IceCube effective area and obtain the predicted observed neutrino events. So, to put a limit on the strength of the attenuation, we will require that the number of observed neutrinos to exceed 6.55 events. This is the 90% confidence level lower limit on the number 13 plus minus 5 neutrinos that IceCube has reported. This leads to an upper bound on the attenuation parameter mu max, defined as the reference cross-section sigma 0 times the column density over the dark matter mass. We compute this parameter mu max for all the combinations of the initial fluxes and the different index cross-sections n. And we also plot the observed neutrino fluxes times the effective area in these plots over here, where the initial neutrino flux times the effective area are in dashed lines, and in solid lines we see the attenuate flux times the effective area. We see here for the cross-section proportional to the neutrino energy, I mean n equal to 1, we can see that the high energy tail of the spectrums are very suppressed. And for cross-section constant with energy, so is n equal to 1, we see that the attenuation is very distributed to all the energy of the neutrinos in all the spectrum. But for n equal to 1 and n equal to n equal to minus 1 and minus 2, we see that the most part of the suppression is in the region of low energy neutrinos. With this mu max over here, we can, using this mu max and incorporating the column density, we can derive bonds on the cross-section as a function of the dark matter mass. Here are the results for the 4 cross-section scalings and 6 dark matter density profiles, considering the IceCube neutrino flux. This is all with the IceCube neutrino flux. We can see here that the stronger limits are obtained with the benchmark 1, as we expected, because the column density is the highest, because the dark matter density profile is the most dense. while the less restricted ones come from the benchmark 3 prime, that is the benchmark with more strong dark matter self-annihilation. We also see that for higher masses, the difference between benchmark 1 and benchmark 3 prime is very small, while for low dark matter masses, the difference between benchmark 1 and benchmark 3 prime is almost 2 orders of magnitude, due to the greater annihilation of dark matter mass, which decreases the column density. Remember that the annihilation of the dark matter decreases the dark matter density profile to a max that is proportional to the dark matter mass particles. So a lower dark matter mass implies more dark matter self-annihilation and a lower the maximal density. Sorry, I'm going wrong direction. So here are the limits for cross-section constant and proportional to the energy. And these are the limits for inversely proportional to the energy and inversely proportional to the square of the energy. So in these graphs, we can see that the boundary regions between the benchmark 1 and the benchmark 3 prime, the limits are region of possible limits. So in these graphs over here, we're gonna show this region of possible limits for all the 4 neutrino fluxes that we consider, and for the different hypotheses on the cross-section. The first thing we can notice is, as in the case of the ice flux, the regions are wider for low dark matter masses than from high ones. This, as we said, is because for lower masses, the dark matter self-alienation further decreases the dark matter density in the spike, reducing the column density. We also see that the regions of the fluxes from SUE and Yang, the red ones and the blue ones, are significantly wider, with a width of about 1 order of magnitude or even a little more. And this is because the emission radius in these fluxes is very small. First, in the flux of SUE et al., the emission radius is very close of the accretion disk, and in the flux of Yang, it's even in the accretion disk. So it's very close to the black hole. So the neutrinos are produced in a very dense region of the dark matter, or in the dark matter spike. So these fluxes are very sensitive to the details of the dark matter spike. The change in the slope or the change in the dark matter self-annihilation has an important impact in the bounce derivative with these fluxes. In contrast, in the model of one, that is the jet cloud interaction model, as the interaction between the jet and the cloud is more far from the black hole, the impact of the dark matter spike parameter is very little. We can see here that the band of the flux of one is very, very narrow. And this is because the emission radius is further out of the black hole. We also see that the strongest limits are obtained with the models are in general obtained with the models of Yang and the models of SUE. This is because of the smaller emission radius that generates a bigger column density, except in the case of the cross-section proportional to the energy, that where the flux of one gives a very strong bound. That is, and this is due to the lower tolerance of this flux to this kind of attenuation. So here can also see the regions for n equal to -1 and n equal to -2. So to conclude, we compare our results with similar analysis based on the neutrino event from TXS known as IC17-09-22A, that is the event of 2017, of September 2017. The IGN NGC 1068 and the tidal disruption event 2019 DSG. Here we show the most stringent bounds, the most strong bounds on each cross-section index using benchmark 1 and fixed the dark matter mass in 1 GeV. Each plot was created with a different neutrino flux hypothesis. This plot is with considering only the IceCube flux. This is only with the XUE flux. This is with the flux of 1, and this is with the flux of 1. The blue and the red limits were obtained respectively using a considering constant and linear energy dependent cross-section. We can see that our bounds are competitive with, or even stronger than the ones from the blazar TXS and the TDEs, but the limits from the active galaxy NGC 1068 are stronger. We also present new limits for inverse and quadratic inverse energy scalings that are relevant for models with the scalar mediators. So, to summarize, we have used the 2014-2015 neutrino outbursts from TXS to constrain the neutrino-dark matter interactions, testing different energy dependence and neutrino fluxes. We present the results as bands as reflect the uncertainties in the dark matter spikes structure. We put competitive model-independent bounds for constant and linear energy-dependent cross-section. We propose new limits for cross-section inversely proportional and inversely proportional to the square of the neutrino energy that are motivated by models with light scalar mediators. These constraints are complementary to other astrophysical probes and are relevant for a variety of theoretical models. IceCube is currently collecting data, now with PyCal GTV and ChemTreeNet, which are beginning to the first observations. This allows us to learn much more. This will allow us to learn much more about neutrinos and how interact with dark matter. So this is an exciting time for neutrino astronomy. So thank you very much for your attention.
Okay, thank you very much for the talk. It was very, very nice. So it is time for questions. So I'm wondering if anybody in the audience would like to ask any question. Nicolás, go ahead.
Yes, thank you very much, Gabriel, for the talk. So I have a question. I was a bit confused at the very end. So you showed this cross-section that scale like 1 over the energy and 1 over the energy squared. That's a cross-section between neutrinos and dark matter, right?
Yes.
But I think you also have proportional to the energy. No?
Yes. I'm sorry.
But how do you have a model where you can realize like cross sections exactly n when n equals to 1? I was wondering how can you realize such a scenario?
Yes. For example, if you have I have the in the bagel slides. I'm going for the. Okay, move this.
You have a very
Okay.
heavy
If you have maybe,
mediator?
for example, if you have a scalar mediator, a scalar dark matter with a vectorial mediator, and you have you can calculate in a very agnostic model, you can obtain this kind of cross section, and in the limit where the energy is low, or if the if the mass of the mediator is very big, you can obtain some cross-section proportional to the neutrino energy. In this
But the
kind of
energy is multi-TDEs, right? So you need a super heavy
yeah, very heavy.
guy.
But it's one possibility also. I mean, we don't know anything about dark matter, so
Okay. Yeah. Okay, was curious about that. Okay, thank you.
no problem.
Any other questions? Walter, go ahead.
So thank you, Gabriel. If you go to page 13, where you have the cascade equation, it was 13 or 14, something like that.
Yes.
Ah,
13.
okay. So this is like one of those integral differential equations, right?
Yes.
Do you have some approximation for the flux inside the integral when you were integrating this, or do you sort of like divide it in a grid this for the or you see like, when you were integrating this, how do you treat the integral of the flux if the flux is the thing that you are solving for?
That's a very good question. We have to make a discretization of the flux to use and we use a method that is based on linear algebra that consists in discretize the flux and the cross sections and try to solve like equation of eigenvalues and eigenvectors. So
Okay.
it's
Thanks.
always a little bit of approximation because you have to discretize the flux and the cross sections and it depends of how many points do you have to point and the time of computation is important. Yes.
Thanks.
Any more questions? For some reason, I'm not seeing everybody. Okay, sorry. Now I see everybody. Sorry?
Carla had a
Nicola,
question.
yeah, go ahead, please. Sorry.
Yeah, thanks, Gabriel, for your talk. Very nice. So,
Thank you.
if I understood correctly, you are taking into account dark matter with masses around GeV or tens of GeV. What about sub-GeV?
What about search?
In the sense, you know that with all the limits that we have for direct dark matter searches, the GeV range is not anymore the favorite. So I wanted to understand a little more what about the new range where people are looking that is the sub-GeV, some in the mass of the dark matter.
We I think we don't focus in any particular range of masses. We only got these plots over here because for nothing special. I think I don't have a very good answer to say why we don't see that kind of masses, that range of masses. That's very good question. I don't know. I'm sorry.
So in principle, you can apply your model and you see which the limits are if the mass of the dark matter is sub-GeV.
Yes. In principle, I don't see any problem. The effects of dark matter self-annihilation will be bigger, but nothing. I don't see anything that could be a problem.
Thanks.
Great. So do we have, let me see if I see everybody. Okay, do we have any other questions from the speakers? From the speakers, sorry, from the audience. Yeah, everything good. So let's see if there's anything by on YouTube. So no questions on YouTube. So I guess that if there are no more questions, then we are okay. So thank you very much, Gabriel, for this very nice talk.
No, thank you for giving me the opportunity of giving a talk.
Yeah, no,
Thank you very much.
it's been great. It's been great. Let me remind all viewers that in 2 weeks we are having a colloquium, not a webinar. It'll be a colloquium by Sasha Karan on some topics related to machine learning and large physics models. So thanks once more, Gabriel, and we'll be seeing you around.
Okay.
See you.
Okay.
Ok, ya estamos fuera del link.
Okay.
Súper, muchas gracias, Gabriel.